This is my design of a jet engine for a hydrofoil or a jet ski, or you can even use it on a small boat. It's fully electrical, fully safe for your toes, and works out of LiPo batteries. I'll go over this design consideration, and the design process. So let's start. So to give some background of why I even started building this is because I just like wakeboarding. And I always wonder to myself, what if I can put a jet engine on the bottom of my wakeboard and let go of the boat and be able to keep going without any boat? Started research online and I found this picture. And you can see it's pretty much the same as wakeboarding, but it's quite above the water. Start looking at these videos that this guy posted, and you can see him here. He designed this propeller system that uses a brushless DC motor, but he actually put it in a hydrofoil that makes it levitate above the water. You can see here, this is a little bit later, this is more recent picture, but this is what he started with. And I didn't really like the construction, looked to me too amateur. I really don't like the open propeller. I do like my toes connected to my feet, so this having an open propeller where you go barefoot sounds to me like a terrible idea. Also, the entire construction seemed a little amateur to me, and some of the gearing wasn't the way I expected it to be. And I decided to change it and to make it more efficient and design my own version of it. So I started first by selecting a motor, and I got to admit I did get my inspiration from his design. But first I looked at what motors exist in the market. And the first thing to understand here is that you need to get a motor that is an in runner. That means that the all the wiring, all the winding or the power is actually on the outer shell of the motor, and the inner core it's what holds the magnet and rotate. There are DC brushless motors that actually has the winding inside and the motor rotates from the outside. They do give you better torque, but thermally they will not be able to handle that. So here I'm coupling the body of the motor to the body of the jet motor, and I use the water to conduct the heat out. So the winding has to be on the outside. And there are different size of motors. And with brushless DC motors, it's pretty simple. The longer it is, the more torque you get. And that's just the rule. You can't get away with it if it's the same motor, same magnets. You want more torque, you got to make it longer. It doesn't matter what kV you have, it doesn't matter what you'll do. You won't be getting more torque in a shorter motor unless there is some assembly constraint or something that makes the longer one less efficient. But basically, longer motor is the same as if you take two short motors and connect them in series one to the other, and they'll just give you more torque at the output. So kind of better to take the longest one you can get and go from there. And you can see here, these are the three different motors. The 83 is 83 millimeter long, 5694 is 56 millimeter wide, and 94 millimeter long, and the 104 is 104 millimeter long. They're all the same diameter, and this is pretty much the constraint. If you want to make something underwater, you can't make it super wide because then you increase the drag in the water. And you can see the torque constant here. So this is unitless if you want to convert to any type of unit, if it's SI or foot-pound or a Newton meter, same as SI, or if you want to do it inch-pound, all you have to do is multiply it by a constant. So to compare between them, the constant is not relevant. But you can see that the smaller motor gives you only 0.181. The bigger one gives you 0.25, and the largest one will give you 0.26. Now, the second consideration on selecting a motor will be to select the current. So at 145 amp, probably reasonable to work at that type of current. 200 amp is not very practical to try and drive. You'll need really thick wires, your losses will be very high, efficiency is going to drop, and you're going to have a lot of complexity in the way you wire stuff. The biggest motor actually only needs 95 amp. And the other consideration is your kV. And there is a lot of misconception about kV. People think, or if you read online, it says that kV is the constant of the voltage that you should give to your motor. And that's not correct, or it's more inaccurate, we can call that. kV is 1 over the back EMF. So what it means is that at 800 RPM, the motor will create 1 volt. What people read online, post online, and see online is that if you want to run at 800 RPM, you need to give it 1 volt. And that's not true. It's the opposite. And I know it sounds like it's the same if it's the opposite, it's one over the other, but it's not. So DC brushless motors work on torque. So the more torque you give them, the more current you give them, you create torque. Voltage, it's actually not what's driving them. Yes, you need voltage to create current, but they go on current. The voltage is the back EMF. And what that means is that when the motor starts spinning due to the current you supply to it, it creates voltage driving back to the controller. And the higher the speed that you're driving the motor, the more back EMF it creates. If a motor has a kV of 800, that means that once it gets to 800 RPM, it will create 1 volt back. That means that you'll need at least 1 volt from your power supply to be able to drive any current to that motor. If you go at 8000 RPM, then you'll need 10 volt to drive the same motor. So this is the voltage that the motor creates as a response to its rotating. And if you just try and just push voltage to it, you basically just going to blow it up because you need to control the current, not the voltage. I know it's a little confusing, but that's the way it works. And you can read more about that. I'm not going to dive too deep into that here. So as I said, I'm trying to get as much torque as I can. And what I really need for that is really the lowest kV I can possibly get. But there's also a limitation to that, because if you go too low, your voltage is going to start rising and you'll need more and more voltage to drive this motor. So I think this 360 kV 95 amp is a good combination. And you can see here the calculation I made. So as you can see, kV is actually 1 over KE, which is the back EMF constant. And back EMF, as I said, it's at what RPM you'll get 1 voltage. So if you take your RPM divided by 360, which is the KV, you'll get the back EMF. And as I said, if you run this motor at 360 RPM, you'll need at least 1 volt to keep running it. Now, this is theoretical. You have some losses. You need a little bit over that, but that's pretty much the way it works. Maximum current, 95 amp. It's a pretty good choice. You can drive that with pretty standard, relatively low cost off the shelf brushless controllers. Maximum voltage, 108 volt. Well, that's not very practical. You don't want to put anything in the water that has 108 volt. Safety voltage is up to 60 volt, so I wouldn't put anything that gets near water that's over 50 volt just to be on the safe side. Now, how does max RPM works? You can see here that this motor has a max RPM of 45,000 RPM. And that's more of the limitation of the bearing and the construction of the motor. And that's also kind of theoretical, because if you take the voltage that they recommend, the max voltage, and you multiply it by the kV, you get an RPM of 38,800. And that is probably the RPM that you will get. You can probably get higher with this motor. The only thing you'll end up destroying it at some point. You have a lot of forces at this speed. You're going to create a lot of vibrations. And it's definitely not a realistic speed for any type of gearing or anything. If you would just create a propeller to this motor and do a direct drive, and there's nothing that's create any vibrations, maybe you can drive at that speed. I don't want to try, and it's really not what I need. So if I use only 50 volt for my application, multiplying it by the kV of 360, my top speed can reach 18,000 RPM, and that will be plenty. As I said, I'm actually more concentrating here on torque, so I want to get to that 95 amp, and I know that my max RPM can get to 18,000 with my power source. Now, even at 18,000 RPM, driving a propeller at that speed, even a jet engine, um, jet that's underwater jet, not air jet, will be pretty bad. The efficiency will be very low. That speed is pretty high for the bearings, and your propeller will be very inefficient. So the good range to go for jet water jet drive is probably between 3 to 7,000, 8,000 RPM. And what I did, I first started looking for gear options that will let me reduce this transmission. And the point is to reduce as much as you can, because the lower RPM, the better. So I selected the gears based on two things. The output gear needed to be big enough to fit on the shaft of 8 millimeters. So you can't go too small, because then you can't put your gear on it. So the gear on the output was a 12 teeth, 8 millimeter shaft gear, with a diameter of 18 millimeters. And the second gear I selected based on the bigger gear that I can fit, that still can fit inside the constraint of the housing without enlarging it for that gear. And by that, what I mean is that my motor is 56 millimeter. I still have the walls, and I wanted a gear that's not going to be much bigger than that. You can see here this gear is 47 millimeter, and that's pretty much what I needed to have it fit inside. And that's a 42 tooth gear, and that gives me a reduction ratio of 3.5. Now, if I take my 18,000 RPM max speed out of my motor, and I divide that by 3.5, I get an output to my shaft of 5,000 RPM. So this was my initial design as far as the drivetrain. First thing, you need to get your drivetrain right, because that will be your limiting factor. You can work around everything else, but if you can get your drivetrain, your motor, your gear right, you really have nothing you can do. You can reinvent physics. If you can get gears, you'll have to create new gears. If you put more than 2 gears there, your efficiency will drop even lower. So that's the first thing that you need to establish before you go further in the design. So once I figure that out, and I know my shaft RPM, and I know the dimensions, I can move to the next step of starting to create the impeller inside my jet engine, and design the housing to house all of that. So I'll go over that next. So once we figure out the shaft RPM, and what motor we need and what gears we need, we can go into the design and putting everything in the box, putting everything in a way that will be maintainable, assemble. You can assemble it in a reasonable effort, and that'll be waterproof, because this thing needs to be underwater. And obviously, it also needs to hold on when you create this thrust. So let's go and look what's inside. So there you go. Let's start. This is the motor that we just talked about. It's size 56 in diameter, length 104. And you can see here that it's connected to transmission. This is the 12 pin. This is the 42 teeth, sorry, Sprouse gear. and from the 12 tooth to the 42, you create this reduction in speed. This is the stainless steel shaft that goes into the propeller. And you can see here, this is the propeller. You can see that it rotates. And let me give you a better view of how the propeller works. Let me make this transparent and also make this transparent. And you can see here, this is the propeller, or sometimes referred to as impeller. Few important things here. So as I said, I do like this design, and I like the jet drive because it's much safer. Some of these hydrofoil or motors are using open propeller, which is extremely dangerous, especially since you're barefoot. I tend to like my toes connected to my feet, as I said. And if you look here, even if you try, you cannot push a finger and reach to this propeller, and that was very important in my design. It's too tight and too long. For anyone's finger, even if you have small fingers, you can't reach it. If you have thick fingers, they won't go in. So this is important. And the other important thing is the out part. So this part services two purposes. One, it protects you. Again, it's too long to put your fingers through here, and it's too tight. But also, it's kind of hard to see, but there is an angle here. And what this does, it takes the circular motion that this creates to the water. So when the propeller turns in this clockwise motion, it creates turbulence in the water. So it's not only pushing water out, it's also spinning the water. And this angler here, maybe it's better seen from this direction. You can see that it has a little band here that catches the water and redirect them. So it takes the angular movement and creates only a movement of the water out in a linear motion in the back of the propeller, eliminating any circular motion. And that's a big problem with boats. It creates a tilt to the boat, it creates a steering issue, and this is how you get rid of it in jet engines. Very common, very important to do. If you eliminate that, your efficiency drops and your steering will, your boat will just go to one side because of that effect, and it'll be very hard to maneuver. The design of the propeller is easy and complex. So the easy part is the step, because the distance from one to the other is basically based on the speed you want to go divided by the RPM, and that'll give you the step size. And that's pretty simple. Your step size based on the RPM needs to be greater than your max speed that you want to go, or at a certain speed you won't be able to push water anymore. So what that does, it collects water and push it out. It needs to go faster than you're actually traveling. In a jet drive, usually there is a reduction stage here to help with that. So even when you do get water and you don't press them or drive them as fast, it will still output the jet at a faster speed than what you're creating. But you still need to be able to drive those water fast enough than your speed. So that will determine your top speed. Now, the how do you calculate the diameter here? That's kind of between an art and a science, and the reason it's not a full science is because that has a lot of variation and a lot of variables. It has to do with the weight, the drag, the weight of the person on top of the surfboard, or the boat. It has to do with many things. And even if you look at commercial boats, the best way to do that is to basically trial and error. So I know it sounds kind of unscientifical, but if you do some research, you'll see that usually you start from a ballpark of what's the pitch. And you start from there looking at more or less you'll usually add a little bit. So on commercial boats, it's usually go between 17-inch to 21-inch pitch, and you just change between them. Here, the pitch I kind of estimated. And the diameter I also estimated. If I'll increase the diameter, it will create more torque on the whole system. So more torque means that you'll have better thrust, that's true, better acceleration, but also more torque on that motor. And I can pretty easily tune that once I start testing it. So far it looks good. I got to my max amp. And the way it works, you do want to get to your max current. You don't want to pass it. So if you get to your max current, which is the 100 amp, you know that you can get full advantage of your motor and that you are pushing all the water you can. If you get to 50 amp and you get to your max speed, that means that you need to increase the diameter here because you want to push more water. Um, so that's pretty much how you test it. And as I said, there's a lot of science here. I'm not an expert in propeller design, but there's also a lot of trial and error, and you can look it up and read about that. Now going to the other parts of the design. So let's talk about the gear here. So let me turn this off for a second so you can see what's going on here. So you can see that the shaft from the motor goes into this gear, it connects this gear. This distance from this gear to this gear is very critical because the teeth of the wheels need to touch at a very certain point because they need to roll on each other and not create friction. So you see there is a special shape to tooth on gears, and that determines the distance between them. So this distance is critical. Now going back into the rest of the design here, so you can see here, let me put back the casing. I designed these to be completely filled with oil, and there is a screw here that you can just take out, fill this whole thing with oil to create as a lubricant for the two gears that touching each other. What oil does, it actually goes on the teeth, and the thicker it is, the more it stays there. And when the two teeth from the two gears are touching each other, it makes sure it creates kind of a layer that let them slide on one each other. The thing is that oil tends to get hot when you do that, and there's a lot of energy here. So even if you take into consideration the 50 volt and 100 amp, it's 5,000 watt of power. Usual gears run at 95% efficiency, so 5% of that, that's a lot of power, and your oil will get very, very hot. So if you just fill a little bit of oil in here, you will burn the oil. So what I did, I put holes in here. You can see here these holes here, and there are actually two more. You can't see it from this view, but they are designed to cool the oil down. So once you put oil in here, you should put it all the way up to here, and it will cool down from these openings, and it will be picked up by this gear and move here to lubricate when they're touching, and will be cooled down by that. And obviously this is all submerged in water, so it'll be nice and cold. The other thing that the oil will do is it will lubricate this bearing. So this bearing can be used with grease or with oil. Oil is always better. Grease is a good solution when you cannot use oil, but grease first tend to fly out when you use high RPM, and also it's more viscous than oil. So oil will give it much better lubrication. So I actually used here a ball bearing that does not have any covers, so the oil will go in and will give it some lubrication. Now you can see there is an oil seal here to make sure that the oil will not go out to the shaft, and there is an oil seal here that actually makes sure that no seawater will go into this bearing. This ball bearing is lubricated constantly by grease or by oil because it doesn't have its own oil pan. So this you can use grease. It's a small one. It doesn't have too much force. This is doing the most of the work. So this one I'm worried about. And when I start talking about this ball bearing, is an angular contact, and what it means is that the balls actually touch. One touches here, one here, one here, and one here, and it's preloaded. So usually you can buy two ball bearings that are angular contacts, and you have to preload them. That means that you need to press them in a way that will create sufficient force on the balls. The thing with that, you can either buy pre-processed bearings that have a very tight tolerance between them, or you need your housing to be very well built, so when you press them it creates just the exact amount of pressure. So as you can see here, I closed my bearing in place just with regular screws, because it's really only holding it in place. So to preload, I bought a preloaded um, angular contact bearing. So this comes completely preloaded from the factory, so you really don't need to do anything. Just put it in place, and it holds a lot of axial force and also vibration force. So that's really a good solution and easy to assemble, and it's not an assemble ball. It's not an expensive ball bearing. Um, really cost a few dollars. Um, I've added one more here just because this is a long shaft, and if you do break one of the fins here, or if you catch something, that can create a lot of vibrations, and I didn't want this to have to carry all this huge moment here. So this just gives it a little bit of an extra support. Not everything is going to be on this. I think here there's like 20 millimeter or something that it'll hold. This will give you almost twice the force. Um, some important considerations when designing ball bearings. Ball bearings needs to be very tight to the housing and the shaft that they're going onto. So the way I did it, you cannot see it in the 3D model, but you will see it if you look at the production drawings. There is plus tolerance, and there is actually a little bit of an extra material here when it touches the ball bearing, and also here. So there is actually some friction there or interference, and this needs to be machined pretty accurately to a tight tolerance. And the way to do it, if you have a machine shop, you'll use a press to put them in. I do not have one. So what I do, I start by putting those two in the oven, let it warm up to 200 degrees. I put this in the freezer and let it go pretty cold. So in about an hour and a half, they'll reach the temperature, and then they will slide in pretty easily. You may need to give them a little bit of a push, maybe with a piece of wood, but they will slide in. After you put the shaft or you put the ball bearing onto the shaft, I let it rest, and then I put the entire assembly in the freezer, and I put this external housing in the oven. When this external housing goes into the oven, it expands a little bit. And this, the ball bearings and the shaft, they shrink a little bit. Leave them there for an hour and a half, and then they'll just slide into place. Or again, you can just push them in with the mallet and have them go into place. So you don't need a heavy press for that. Pulling them out is usually easier. Next, let's talk about the construction as far as water tightening. So to get everything watertight, that's quite the challenge. You got to think about how everything will be sealed, and it needs to be assembled and disassembled, and it needs to be machined to manufacture it. So there are a lot of limitation of things you cannot do. And as you can see, to make it watertight, I used aluminum body to anything that has watertight contact to it. The only thing that is watertight but not aluminum is this piece, which is 3D printed. And the trick here is that this is 3D printed. You run your wires through this hole here, and once you run the wire, you put epoxy inside this hole to completely encapsulate the wires, and no water will go through this hole because it's filled with epoxy. Now, when you want to get this watertight, what you do, you close this screw from the outside, and this screw will push this piece in, and this piece will push on this O-ring, which will make it expand and press through the wall and through this part. So that will not let water in. So this is on this side, and this is something that's a little tricky to get done right, but you really have no other choice on this end, because you don't want to put any screws on this direction. Um, Over here, you can see that the motor housing, um, let me get a better view. So here there is kind of a lip here, so you can get the O-ring, and this is the O-ring here, and you can see that all the screws are on the outer side, so the O-rings does not interfere, or the screws, sorry, do not interfere with the O-ring. So even if water will go in here through this thread, they cannot go inside because the O-ring is here. And you can see even if water will go from here, they will stop. Now, the trick when you do this type of thing is to make the O-ring that is actually oversized to your groove, or actually make your groove a little shallower than the O-ring. So if this O-ring is 1 millimeter or 1.5, I can't remember right now, the groove depth is only 1. However, you gotta let the O-ring have space to expand. So this groove is much wider than deeper. So when you do compress it, make sure you calculate that to have enough space for the entire O-ring to be contained within the groove. If you just compress it and it has nowhere to go, it will actually create a gap between your parts, which doesn't look good and doesn't perform very well. Same here, you can see the same thing. The O-ring is compressed here, but it has a lot of space to expand on the outside. You can see the O-ring goes through here as well. And if I'll make this thing, I'll remove this again. You can see how everything is constructed in here. Let me remove this so you can see how the O-rings are built here. So you see this is actually an O-ring that was stretched around that. And another trick when you are doing something like this, make sure your O-ring is a little bit shorter than the actual length that you need it. It just makes it easier to assemble, because then you can snap it in. If it'll be the exact same length as your groove, you're going to put it in and it's going to just fall out. So if you make it just a little shorter, you can snap it in and you can assemble that. That makes it much, much easier. Regarding material selection, so let me put this back on first. The material selection, as I said, this is aluminum, this is aluminum, this is aluminum, this is all anodized, so it doesn't get any type of corrosion. The shaft that goes outside this shaft is stainless steel. It's 316 marine grade stainless, and that's just because this part is exposed to salt water, and it needs to be strong, so it cannot be aluminum. So I want to make sure that it will hold the test of time. And the housing, the jet housing, the jet nozzle, and the propeller were all designed in a way that they can be 3D printed. And I experimented with both ABS and with onyx. That's a type of nylon, reinforced nylon. And because of the design, if you see, there are some support structures here. There is some angles that gives it some more force. This holds just fine, and I put it to the max torque, and it holds really nice. So that makes it very, very cheap to print in any good 3D printer, and you don't need to spend any money on machining, because machining a part like that will be super expensive. So this is one part, this is one more part, this is another part. Let me remove this. You can see how the propeller is built. And this is, as I said, 3D printed, so very, very cheap to make, very easy to make. Um, the other parts that are 3D printed is 1, 2, and 3, and I made them a different color just because these can be printed on any cheap printer. There is really no structural importance to this part. This part just makes the whole thing more aerodynamic, so it just makes sure that the water will just flow smoothly around that. These are just supports to hold it to the board. There is a blind thread here, so you can put a number 6 screw through your board into here. So these have no structural importance. I just print them on a very cheapy PLA material, very, very low cost. You can print them on $100 printer at home. Um, Now the other trick here is thermal, and that's very important consideration. So if you remember when I talk about the motor, I said that the importance of using an inner rotor motor. So this rotor, the shaft moves and there are magnets inside that runs. And the outer shell of the motor is connected thermally, mechanically and thermally to the aluminum body. And as you can see here, there's actually a little step here on the body, and that's just to make sure that there'll be really good contact between the body and the motor. So you can see this is the motor, this is the body, it's very tight. And you really want to almost have it in a way that you need to push it inside, but you don't want to push it through the entire distance. And that's why this is wider than the last part, because you really want only the last part to be hard to push. If not, it can be a real nightmare to push this thing every time in and out when you need to do any maintenance or repair. And this is aluminum, which can start getting deformed when you push it too hard. So you really want to give a little bit bigger opening here and tighter opening here. And again, not too tight, give it maybe 0.1 millimeter gap, and then you can fill this gap with thermal material. My controller, the electronic controller, the ESC, the brushless motor controller, sits on this heatsink, and this heatsink sits connected to the enclosure. So this is aluminum, so the heat from the electronics, it's not modeled here, but the heat just goes from here to the body and then to your lake or seawater or whatever, and it just gets cooled. So the whole system is very, very cool. Nothing gets too hot in here. I tested it, works even better than I expected. When you got water, water is a great way of cooling stuff, and there are other designs. Most designs actually use a pump to pump water into the surfboard, into the controller. Doesn't make sense. Just add more complexity and lowers the reliability. Just put the controller here, and it's close to the motor. It has a good thermal conductivity out, and since it is close to the motor, so all of your high frequency three-phase to the motor going for a very short distance, and all you have to go back is your 2 battery leads, which do needs to be thick, but they need to be thick anyway, and 1 tiny control wire. So that's a big advantage of my design over other designs. Overall, you do need a good machine shop to make all these parts. Um, Everything here was designed that you can make it on a 3D lathe, 3-axis CNC and a lathe. There is no crazy 5D machining here and things that you need some crazy technology. Pretty standard equipment to do all that. So it looks complicated, but it's actually designed to be very manufacturable, and you can do it in any good machine shop. But you do need a machine shop. I don't think you can do it at home unless you're really, really good at machining stuff. So that's all. That's all I have. If you have any questions, leave it in the comment below, and I'll try to answer.